In this film, we've been looking mainly at static electricity and seeing how it can be generated. The next film is the first of two which demonstrates how electric current can be generated in the laboratory and in the giant power stations which provide the electrical energy on which modern life so much. In this film, we've been looking mainly at static electricity and seeing how it can be generated. The next film is the first of two which demonstrates how electric current can be generated in the laboratory and in the giant power stations which provide the electrical energy on which modern life so much. This is the first of two films about the electricity industry, about the generation and transmission of electricity. We shall explore modern power stations and find out how they work. But first of all, some laboratory experiments showing the basic principles. Electricity can be generated by taking advantage of electromagnetic induction. Move a magnet in and out of a coil of conducting material, and a current will flow in the coil. There's the magnet, and there's the coil. The coil is connected to a sensitive galvanometer. Watch what happens. A current flows in the coil only when the magnet's moving. When it's still, no current passes. Here's another magnet, a permanent magnet, like the one we've just used, but a different shape. We're going to make up a simple electrical generator using this magnet and this single turn of copper wire. It's fixed on an insulating handle and connected to the galvanometer. If we just move it around between the poles of the magnet, again a current passes through the copper wire just as long as it's moving. If we rotate it like this, we get an alternating current, which changes its direction, first flowing one way, then the other, as the coil's rotated. But of course the wires get all tangled up. This is what's happening. When the loop's moving through this position, the current flows down the right-hand side in this direction. But the loop continues to rotate, and when that side has come across to here and is moving upwards through the magnetic field, the current induced now flows in this opposite direction. So, as the loop rotates, current passes first in one direction, then the other. An alternating current is produced. The current along the yellow lead is first traveling one way, then the other, as the loop turns. While that along the black lead is always flowing in the opposite direction, first one way, then the other. Here it is again. Using just a single turn of wire, we get only a very small current, and as we saw before, the wires got all caught up in a very short time. So we can use this device. The same single loop of copper wire, but one end's connected to this copper ring on an insulating spindle, while the other's connected to the second copper ring. The insulated connecting wire passes underneath the first ring, then it's joined to the second one. These are called slip rings. We mount this device so that it can be turned by a crank. Each of the two rings brushes against a metal strip, so that there's electrical connection between the loop as it rotates and two terminals down at the bottom. Each end of the loop is always connected to the same terminal. We've now made an improved alternating current AC generator, although the EMF it produces is still very, very small. The galvanometer needle shows us that it is AC alternating current, changing its direction regularly as the coil's rotated in the magnetic field. Remember, there's got to be constant movement to keep the current flowing. Instead of using this sensitive galvanometer, we can show that we are generating alternating current by using a cathode ray oscilloscope, set so that it draws for us the current produced. A sort of wave, moving up and down as the current changes direction. You can see how the current goes first positive, then negative, and then positive again, and so on. Here's a different arrangement. Instead of the slip rings, the two ends of the same copper wire loop are now connected to one of two split rings, which are separated by an insulating strip. This is called a commutator. In this position, you can see how the right-hand side of the loop is connected to this terminal, while the left-hand side's connected to this one. When it rotates, the right-hand terminal is always connected to the side of the loop which is moving upwards, while the left-hand terminal is always connected to the side moving downwards. So current taken off from the two terminals will always be flowing in the same direction. And the galvanometer shows that this is so. We've now got a direct current, a DC generator. The cathode ray oscilloscope draws the pattern as before, and you can see that this time the trace never falls below the line. This is direct current. There it is. The trace never dips below the line, never becomes negative, that is, never flows in the other direction. This is a more useful generator, although it's quite a small one. The magnet's now an electromagnet, and the coil's much more complicated, but the principle's just the same. We're turning mechanical energy, turning the crank, into electrical energy. Watch what happens when we start using electricity to light the lamp. The handle's harder to turn. Switch off and it's easy again. When the lamp's on, we have to supply more mechanical energy because more electrical energy is required to produce light and heat energy in the lamp. To produce electrical energy, you have to provide mechanical energy. It's all a matter of turning one kind of energy into another. You never get anything for nothing. We're now going to look at electricity generation on a much bigger scale, but the same applies. We've got to provide other kinds of energy to convert into electrical energy. The source of energy at many power stations is coal, and we'll start at a very big coal-fired station in the northwest of England. This train's bringing 1,000 tons of coal, and it won't last long, as we'll see. It's unloaded, then taken by mechanical conveyors to the coal stacks. Burning this coal will provide energy, which in the power station will be converted into electrical energy. From the coal stacks, the coal is carried up to the boiler house. It's first fed to great mechanical grinding mills down at ground level, which turn it into a very fine powder. This is just one of the grinding mills which work 24 hours a day, pulverizing the coal. The powdered coal is next burned. Chemical energy is released as heat energy in the boiler furnaces. Here's a simplified diagram. The furnace is like a giant hollow box with pipes running up inside it. The heat from the burning coal boils water in the pipes, the boiler tubes, turning it into steam, which passes out through the pipes at the top. This steam, superheated to a very high temperature, passes along pipes to turbines. Here, mechanical energy is produced as the steam makes the turbine blades rotate. This mechanical energy of rotation is turned into electrical energy by the generators. A big electromagnet, the rotor, rotates inside a system of coils, the stator, and produces alternating current, which can be sent out over the national grid system. The steam which has passed through the turbines is turned back into liquid water in big condensers underneath. The steam is cooled by cold water, passing through pipes. The condensate, the water, passes out at the left there, back to the boilers to be turned into steam again. We don't turn out anything like all the energy as electrical energy. A lot is unavoidably wasted as latent heat in the conversion back to water, but it's made as efficient as possible. Air is needed to burn the coal. It's drawn in from outside, and here's one of the huge ducts down which it comes. Each of the 4 boilers has 2 furnaces, supplied with air in this way. There's one of the big electric fans which draw in the air. The coal dust is blown along these orange-coloured pipes to be injected into the furnace. Every 10 minutes or so, a ton of coal is burnt at each burner. There are nearly 200 coal burners in the station as a whole. Here are just 2 of them. You can sense the great heat produced inside the furnace as the coal burns. Well below, at ground level, ash is falling from the burning coal above. You can see some of the boiler tubes, in which water is turned into high-temperature steam. Right at the bottom of the furnace, the biggest lumps of hot ash collect. The coal is burned up at a tremendous rate. In just 2 minutes, the 32 tons of coal in a railway wagon are used up. This giant shovel picks up 15 tons of coal, less than a minute's worth. Every hour for 24 hours a day, a trainload full, 1,000 tons of coal can be burned to make 2 million kilowatts of electricity at this one power station. An enormous amount of energy is consumed. The boilers and furnaces are enormous. Here we're looking down to the bottom. The boiler towers for 200 feet. And the superheated steam emerges in pipes from the top. All operations are controlled from here, the power station control room. Here are the instruments for just one of the 4 turbo generators. Steam is coming from the boiler at about 560 degrees C. It's led down these pipes to the turbine hall, where the electricity is actually generated. This is one of the 4 sets of generating equipment. This is where the steam enters the turbines, and the mechanical energy is produced to drive the generator. The steam's at over 400 degrees C as it enters the first high-pressure turbine. There's a chain of turbines to each generator. The noise is almost deafening as the turbines race round, driving the big generator. The generator housings are painted orange, and you can see them quite clearly. There are 3 other turbo generators in this great hall. Each generator at this station produces 1/4 of the total output. In the control room again, there's a great array of instruments and controls for each of the 4 generators. Each is sending out over 450 megawatts of electrical power. The station as a whole generates 2,000 megawatts, 2,000 million watts of electrical power. The power is carried from the generators to transformers and switchgear outside, then passes out to the national grid. A large number of power stations, getting their energy from coal or oil or running water or from nuclear reactors, feed electricity into the grid, which provides electrical power throughout the land. In the next film, we look at the way in which electricity is transmitted. And we'll look, amongst other things, at another way in which heat can be raised to produce steam to drive turbo generators. This station turned the chemical energy of coal into electrical energy. We shall visit a generating plant where the energy doesn't come from burning a fossil fuel like coal or oil, or from running water. Here at a power station in North Wales, heat produced by changes happening in the very heart of the atom, the atomic nucleus, is harnessed to produce electricity. We'll visit this nuclear power plant and find out some of the differences and similarities between a generating station using the old fuel and one using the new. In this film, we'll find out more about what happens in modern power stations, and we'll look at a quite different way of providing the energy needed for the generation of electricity. Many power stations depend upon burning fossil fuels, coal or oil, to raise steam to drive the turbo generators. Here at Wilver, on the Anglesey coast, there's one of Britain's nuclear power stations, which depends upon a very different process. This is the roof of the huge building which contains 2 nuclear reactors. Inside, there's a vast open space with the tops of the reactors visible at each end. Here's one of them. In the control room, engineers keep strict control of the processes going on in the reactor, so that it provides just the right amount of heat to raise the steam needed for the generators in another building. Each end of the control room looks after one of the 2 reactors. Inside the reactor, gas is being heated up to nearly 350 degrees C by the nuclear reactions taking place there. Screens display the temperatures in different parts of the reactor. This is a sort of plan view, showing what's happening deep down inside the reactor. What does the fuel look like? There are nearly 100,000 of these fuel elements in the two reactors. They contain uranium and only heat up when they're all placed in exactly the right pattern inside the reactor. These fins are there to hold them in place. Gas circulates around the elements, taking the heat away as it passes along these grooves on the surface of the casing. Here's a simplified diagram of the boiler arrangement. There are boiler tubes through which water passes, separated by a shield from the reactor. The reactor produces heat, and gas circulates around the fuel elements, carrying the heat to the tubes, so that steam's produced and passes out to drive the turbines. The gas used to transfer heat from the reactor to the boiler tubes is carbon dioxide, CO2. It arrives at the power station in big tankers carrying the liquefied gas, and it's stored in tanks until it's needed. The reactors are each enclosed in thick concrete shells inside the reactor building. There's no noise coming from it, but it's generating heat by nuclear reactions going on in the fuel elements and producing steam like the coal-fired boilers we looked at in another film. This steam passes through pipes to the generator building. In the control room again, we can see the temperature of the steam coming from the boilers. It's about 320 degrees C. There are no chimneys because a nuclear reactor produces no smoke, so there's no need for the big electrostatic precipitators we saw at the coal-fired station. But in fact, a lot of small precipitators are used in a nuclear power plant. Here are some of them at Wilver. They're to test the carbon dioxide which is circulating around the fuel elements in the reactors. If an element should develop a fault and particles of radioactive solid got into the carbon dioxide, a precipitator would collect these solid particles just as if they were ash particles in smoke, and their radioactivity would be detected. This would show that something was wrong in the reactor, and the right steps could be taken to prevent any damage. Instruments in the control room show if the precipitators are picking up any radioactivity. This is just one of the precautions taken in nuclear power plants to make them safe as well as efficient. But many of the instruments in the control room are like those in, say, a coal-burning plant, because it's only the way in which the steam's produced that makes nuclear power stations different. The steam's used to drive turbines which drive generators, just as in all power stations. Here's a gauge showing us the turbine speed, around 3,000 revolutions per minute. And here we are in the generator hall, where the electricity is being produced. This is a smaller station than the coal-fired one, but it still produces 1,000 million watts of electricity. Let's look at the generating equipment. Here's the inside of one of the turbines, removed for servicing. You can see that there are many sets of blades. These are turned by the hot steam expanding through the turbine housing. The same kinds of turbine are used, however the steam's been generated, in a coal-fired boiler, say, or in a reactor, as here at Wilver. There's a turbine like the one we've just seen inside this casing, driven by high-pressure steam straight from the boiler over in the reactor building. The steam emerging from that first turbine then passes to low-pressure turbines, all helping turn the same shaft. The big pipes above carry this low-pressure steam to these turbines. The turbines do the same job as the crank in that laboratory demonstration in the last film. They drive this AC generator, which consists of a big electromagnet rotating inside an arrangement of coils. The electromagnet rotates, not the coil as in the lab model, but the effect is the same. The model used a permanent magnet. The big generator uses an electromagnet. So there has to be a sort of mini generator, called the exciter, to power this electromagnet. Here it is at the end of the shaft. All modern power stations have sets of turbines driving generators. We've seen the same kind of equipment in use in a big coal-fired station in the earlier film. Our lab demonstration model produced only a very small current, led by quite thin wires to the galvanometer or oscillograph we used to detect it. Power station generators produce vastly more electrical current. Here at Wilver, you can see the casing round some of the cables, taking the current out from the generator hall. After raising its voltage, we'll be coming to that in a few minutes, the current is led to the pylons which carry it across the country in the national grid system. At Wilver, there are some noticeable differences from coal-fired power stations. For one thing, no railway tracks. 1,000-ton coal trains aren't needed every hour, as they are at Fiddler's Ferry. Quite apart from the trains and the great coal stocks, there are these giant cooling towers at our other power station. What are they for? Do you remember that when the steams pass through the turbines, it's cooled in a condenser to turn it back into water to be returned to the boilers? The condenser circulating water coming out at the top has to be cooled so that it can be used again. It's this condenser circulating water, not water coming from the boilers and the turbines, which is cooled in the cooling towers. These are great hollow concrete chimneys of a special design, as we'll see. A lot of water gets lost as water vapor from the tops of the towers, so there's got to be a constant topping up with water from, say, a nearby river. Inside the towers, the condenser circulating water falls like rain, and it's cooled by a current of cold air passing up the tower. The water came out from the condenser at about 30 degrees C, and this cools it to about 20 degrees C, ready to go back again. The water is sprinkled down from about a third of the way up the tower. Above this, there's just a great hollow space. The sides are curved inwards near the top, and it's this particular shape which produces a constant flow of air drawn in at the bottom and out at the top. Cooling towers are a prominent feature of many inland power stations. However, because Wilver is by the sea, there are no cooling towers, and seawater is used to condense the steam coming out of the turbines. It's returned to the sea when it has passed through the condensers. This does no harm to marine life. The condensers are underneath the turbines. Now all this means that a lot of heat's wasted in a power station. That's one reason why you only get about 25% of the heat energy produced in the Wilver reactor turned into electrical energy, while a coal-fired station can turn about 35% of the energy of the coal into electricity. This loss of heat can't be avoided. It's a basic law of physics. Think of all the heat wasted from the top of the cooling towers, for example. There's another kind of waste from a coal-fired station. Thousands of tons of ash are produced every day. This is removed from the precipitators, mixed with water, and pumped along pipes into huge lagoons lined with concrete. As the solid matter settles out, the water can be pumped off and used again. Eventually, the lagoon's filled up with ash, and all the water's taken away. Huge deposits of waste are left. One of the big problems about burning coal is not only the cost of the stuff, but what to do with the thousands of tons of waste ash that's left. Some of it can be sold, for road making, for example. Here's work on a new motorway interchange, and they're using many lorry loads of power station ash, but there's not nearly enough road making to use up all the ash that's produced. Making electricity means using up other fuels. The power goes out across the pylons, and each one of these empty wagons means that 30 tons of coal have been used up. The scene at a nuclear power station is very different. Each fuel element lasts up to 2 years and can then be reprocessed to provide more material for the nuclear industry. A road is all that's needed to bring in fresh fuel occasionally and remove waste. But the waste is radioactive, and great care must be taken with it. This model demonstrates an important feature of electricity transmission, sending it out to where it's needed. Look at these two lamps, one shining much more brightly than the other. Let's look at the power station end. The same current's fed to two lamps, which shine equally brightly. It's also fed at a voltage of 6.5 volts along one of two transmission lines. Now, when electricity passes along a conductor, some power gets wasted in heating the wire, and the longer the conducting line and the higher the current, the greater the loss. So see what happens at the end of our line. The bulb glimmers only feebly. A second line is fed through a transformer which raises the voltage to about 83 volts. Much higher than before. The line's the same length as the first one, but there's less power loss at a higher voltage because the current is smaller. It's transformed down again to 6.5 volts, and because there's been a smaller loss, the lamp shines much more brightly than the first one. Compare the two. The lamp fed along the high voltage and therefore low current line is much brighter. Here's a demonstration transformer. It has a soft metal core, and we'll surround one side with a primary coil of 1,200 turns of wire connected to the 240 volt alternating current mains. Then first, we'll put a 5-turn secondary coil on the other side. We complete the iron loop so that it's continuous and connect the secondary coil to a voltmeter. Read the top scale. We get a voltage of just less than 1 volt from the secondary coil. Now we put on a secondary coil with 10 turns. We get a voltage of nearly 2 volts from this secondary coil. Finally, a secondary coil with 15 turns. This gives us a secondary coil output of nearly 3 volts. You can work out the connection between the primary coil voltage, the number of turns in the 2 coils, and the output from the secondary coil. This was a step-down transformer, reducing the voltage. Transformers at power stations are very much bigger. They're used to step up the voltage from the generators to a much higher value to reduce power loss in the long transmission lines of the grid system. Here, it's been stepped up to 275,000 volts. It's sometimes transmitted at 400,000 volts over the supergrid network. The voltage can be stepped down by other transformers at substations along the line, and then distributed to the houses and factories and so on where it's used. In Britain, the railways use enormous quantities of electrical power. The overhead electrification system carries electricity at 25,000 volts. Inside the locomotives and other traction units, this has to be transformed down before it's supplied to the driving motors. So, transformers have to be fitted. At British Rail Engineering Limited, Crew Works, a big transformer's being fitted to a locomotive.
Ready?
It's a very heavy piece of equipment and takes up a lot of space inside the locomotive.
Whoa.
But it's worth doing things this way because the disadvantage of the extra weight to be carried is more than made up for by the greater efficiency of electric power distribution at a high voltage. If the system was supplied at a low voltage, the transformers wouldn't be needed, but then there'd be a great waste of power in the long overhead wires. Another good example of physics in action. Modern industrial nations must have electrical power for transport, lighting, running machinery, and many other purposes. To produce that power, other kinds of energy must be used up. You can't get anything for nothing. Coal burning is expensive, produces a lot of waste, and coal won't last for very much longer. Oil and gas will last for a much shorter time. Nuclear power may be very important in the future. Many people are afraid of it. Try to understand it. The advantages and people are afraid of it. Try to understand it.